Hello, welcome you back for the lecture 4, which is going to delivered by Dr. D. Srinivasarao, who is Associate Professor of Department of Electrical Engineering, NIT Warangal. I'll try to introduce today's speaker. Dr. D. Srinivasarao was born in Andhra Pradesh, India. He received his BTech degree from Bapatla Engineering College in 2006. He received the M.Tech and PhD degrees in electrical engineering from Indian Institute of Technology, Roorkee, in 2008 and 2014, respectively. He is currently working as an associate professor with NIT Warangal, National Institute of Technology, Warangal. His research interests include power quality, multi-layer inverters, modulation techniques for multi-layer inverters, development of new converter topologies, electric vehicles, and adjustable speed drives. He has published more than 20 research papers in various journals and presented more than 10 research papers in various international conferences. He has supervised 3 PhD scholars and guided around 50 graduate and undergraduate student projects. He has delivered more than 200 lectures in various conferences, workshops, and short-term courses. I thank Dr. D. Srinivasarao for accepting our invitation and delivering the lecture. I'm handing over to Dr. Srinivasarao. Sir, DSR, sir, you are not audible.
Am I audible to you now?
Yeah, audible now, sir.
Oh, thank you. So let me share my screen. So today we will discuss about some of the advances in power converters, so especially used for the grid level. So first we'll start with the basics of power converters, and I will give you some overview of some power converters and high power converters. So next we'll discuss about the multi-level converters and their PWM techniques. So followed by, so we'll discuss about the reduced switch count multi-level inverters and the different types of topologies and their PWM techniques. Right. So you're aware that, right? So power converter is an essential for all kind of applications, especially grid connected applications, motor drives and all. So you must require a high performance and cost effective converters for, it's a prerequisite to realize any power electronic application. So in an industry, so it is necessary to control the output voltage of the converters. The first thing is to cope with the variations in the DC input voltage. So next thing is that to regulate the output voltage of the converter. And in case of motor drives, so we need to satisfy the V/F ratio, right, to keep the air gap flux constant in case of motor drive systems, right. In case of applications, especially for grid connected applications like StatCom or for integration of the PV, renewable energy sources or any other thing, right? So in that case, so we need to operate the power converter as a controlled current source or a controlled voltage source, right? So for that also the control of power converter and its control is necessary. So there are variety of applications so which require power converter. So one is the adjustable speed drives, so that is motor control. So next one is the hybrid and electric vehicles. So this also requires a power controllers, especially in case of electric vehicles. You require one power converter for the charging and another power converter for the drivetrain. So FACTS, flexible AC transmission systems. So this is second generation, especially these are based on the self-commutated devices like StatCom, uh, dynamic voltage restorator, also no, sorry, not triple SC and UPFC, so that require the power converter circuits. Also, these custom power devices are at the distribution level, so like such as DStatCom, DVR, UPQC. So these also require some power converters, active power filters, renewable energy sources. Like for this renewable energy sources, for integration we require one power converters for generation also, like solar PV, MPPT, converting that DC voltage to higher DC voltages, and the DC is converted back to AC. So you require uh, power electronic converters. HVDC and HVDC plus. So HVDC is based on the GTO technology, and HVDC plus is based on the modular multi-level converters, MMC. Right. So these also require power electronic converters. So grid connected transformer applications. So nowadays we can increase the level of means you can increase the voltage and power level of power converters, so that we can directly connect to the grid. So without using a transformers, we have some converters are there. We can directly connect to the 11 kV grid. In case of HVDC, we can directly convert to connect it to the 230 kilovolts AC grid. Right. And battery chargers, so all kind of battery chargers, starting from the mobile battery chargers to the electric vehicle battery chargers or the energy storage system battery chargers, so that all require these power electronic converters. So home appliances like the air conditioners, washing machines or some handheld tools require some power electronic applications or power converters, so ranging from a few watts to several kilowatts. So you're aware that, right? So power converter consists of different things, right? So usually this can be divided into two types. So one is the direct conversion, and another one is the indirect conversion. In case of direct conversion, we have AC to AC conversion. So here the input is usually fixed one, and the output AC will be vary. We can vary the amplitude and as well as the frequency. So cycloconverters used early days, right? And later on we shifted to the matrix converter, right? Cycloconverter based on the thyristors, so whereas this matrix converter is based on the self-commutated devices like IGBT and MOSFETs, right? So we have this indirect conversion. The first step is that AC first converted to DC, and DC is converted back to AC with the required amplitude and the frequency. So there are two options are available. So one is voltage source inverters, and another one is the current source inverter. So also known as the VSI and CSI. Right. So current source inverters are relatively less popular. So when compared to the voltage source inverters, so current source inverters, again there are two types are there. One is the load commutated inverters. This load commutated inverters is based on the thyristors, and we have this PWM current source inverters. So these are again based on the IGBTs or MOSFETs. So in case of voltage source inverters, so which is very popular nowadays, right? So we have two level inverters are available, right? And so multi-pulse inverters are available, and the multi-level inverters are available. So this multi-pulse and multi-level inverters are for the high power and medium voltage applications. In case of multi-level inverters, there are varieties of topologies are available. So one is the flying capacitor, neutral point clamp, and this cascade edge bridge are the popular ones. So, and also later on, the several inverter topologies are introduced. Right. So mostly these are by changing the circuit device here and there. So every time they will develop some new converter topology. So we'll discuss that thing in the later point of our in this section. So as we discussed, in case there are two types of inverters so that are commonly used, and the voltage source inverter and the current source inverter. So as I mentioned earlier, so this voltage source inverters are very much popular when compared to the current source. Okay. There are several factors for this one. The first thing is that so we can obtain this DC voltage source from a battery or from a regulated power supply or from a capacitor or some PV. So we can obtain this DC power supply or voltage source here. So whereas in this case, so we need to keep this current constant, right? So this kind of current source is not readily available. So only thing is that we will connect some DC source with some large inductor, so that will form a current source, right? So that is one of the drawback here. And when compared to that, so we need to connect a large inductor, the size of the inductor, and it will makes heavy, and the circuit are also bulky, and it will also produce more losses in the circuit. Right. So another thing is that so here uh, in case of voltage source inverter, so switching losses are relatively less. So why? Because in this case, either the current will flow through the IGBT or MOSFET, or it will flow through the diode during the freewheeling time. So whereas here, so every time the current will flow through the both switch and as well as the diode. So therefore, we can expect that the losses are relatively high. So if you compare the merits of current source inverter, so one is its short circuit protection. So even though when it is short circuited, the maximum current is equal to the source current, right? So whereas here, if some short circuit is occurring here, so here, so this resistance are relatively low. So that means we can expect that a huge current will flow through the devices, and that may lead to the damage. Right? So to prevent that, so we need to make sure that the two devices in the same leg should not be turned on simultaneously. So we need to provide some deadband or some blanking time between these two devices. Right? So we have to ensure we have to for example, one top device is conducting. So before turning on the bottom devices, so we need to wait until the first device or the top device is completely commutated. Okay. So what we observed that is that voltage source inverters are more popular, right, due to many factors. One is the efficiency, size, and popularity wise, right, compared to the current source inverter. So you know that, right? So if you use this voltage source inverter, so we can control the output voltage by using some PWM methods, right? So there are two types of control is possible in inverters. So one is the voltage control, and another one is the current control. So in case of voltage control, we normally use the PWM methods like sine PWM method or the space vector PWM method or the selective harmonic elimination PWM methods. Okay. In case of current control, so that means if you want to operate the inverter as a controlled current source, in that case we normally use a triangle carrier current control method or the hysteresis current control method. Right? So depending on the operation or application, sometimes we use it as a controlled voltage source, or sometimes we use it as a controlled current source. Okay. So if we let us assume that, so we are using a sine PWM technique, so which is very popular. Right? So consider the amplitude modulation index, so which is 0.95, and the frequency modulation index, that is 20. So that means it is operating at 1 kilohertz carrier frequency. Right? So you can see its harmonic performance. Here the harmonics are centered at around MF frequencies and 2 MF frequencies here, and so 3 MF and so on. Right? So here this MF is corresponding to the frequency modulation index. Right. And you can see that the THD is around 75.26, and this waveform is nowhere close to a sinusoidal waveform, right? So to make this sinusoidal, so we normally connect some filter circuits. So commonly used filters are this kind of LC filters or the LCL filters. So if you are using these two, so that is becomes LC filter, or if you are using these three, so two inductor and capacitor, that will become LCL filter. Also, we have these LC filters, so that are commonly used. Right. So most Common used filters are the LCL filters. So LCL filters are most commonly used. Right? So these filters will suppress the harmonics at different levels, and it will make this voltage waveform as close to a sinusoid as possible. Right? So another thing is that by adding some these passive components like inductor and capacitors, so that will increase the losses in the converter, and as well as it will also include some weight. And another thing is that if you are including some capacitors, right, so that will also increase the failure rate of the inverter. Yeah. So for example, if you are going for a higher voltage levels, like some high voltage level applications, so in that case, so what we can do is that, so instead of using a single switch here, so we will use multiple switches in series to increase the voltage level and to increase the current level. We need to connect several switches in parallel, right? So here, why we need to use several switches here? For example, in this case, let us assume that this DC voltage is VDC. So each switch here is supposed to block a voltage of VDC. This switch is supposed to block a voltage of VDC. So both all six switches is supposed to block a voltage of VDC. For example, you know that, right? The fundamental thing, if you are using a sine PWM technique, and if you require 415 volts on the output side or 400 or 440 volts on the output side, right? So we need to select this DC voltage such that this will be, so 415 volts by 0.612 times. Like if you require a line voltage of this much, 415 volts, so you need to select a DC link voltage like this. If you are using a sine PWM technique, similarly, if you are using a space vector modulation techniques, so you need to use 415 by 0.707. So that means that's how this DC link utilization is moving in case of space vector modulation. Right? So that means each device is supposed to block so this much voltage. So if you are selecting an IGBT or MOSFET, so the switch must be supposed to block so this much voltage, right? So if you are keeping some factor of safety, for example, 1.6 times or 2 times, right, it will be 415 by 0.612, right? So that is the minimum voltage that requirement. And if you consider some factor of safety, so that will be this much, 1.6 or 1.8 or 1.2. So this much voltage is supposed to block. And if you see that the different manufacturers, so they normally produce the voltage ratings of different things, like 600 volts devices are available, 800 volts devices, and 1 kV, 1.2 kV devices, 2 kV devices, or 1.7 kV devices, like 3.3 kV devices. These are the devices are available in the market. Okay. So based on that, so what is the nearest value? So that device you're supposed to select. So if you want to select the current rating, right? So the current rating obviously depends on the load side. So how much current is handling? So like 50 amperes or 100 amperes. So that based on that you can select the current rating. But the basics for the voltage rating is that, so how much voltage you are expecting on the output side of the inverter, right? So based on that you need to choose the input DC voltage, and if you are keeping some factor of safety, and accordingly you can select the switching device. So let us assume that you are using it for a high voltage application, right? So let us assume that you are connected to some high voltage applications like somewhere between 11 kV grid or 3.3 kV grid, but directly integrating to that. So that is obviously it is a normal thing, right? Our distribution lines is at the 11 kV, right? So still, if you are using a 415 volts converter, right? So you normally require a transformer between 11 kV and 415 volts transformer, right? So that is one choice. So another choice that we can directly connect to a 11 kV grid. So that means we can rate this converter to 11 kV. So if at all you want to rate this to 11 kV, so what are the things you need to consider is that, so here this point, let us assume that this grid side, this is 11 kV. So line voltage RMS value. So accordingly, this DC voltage will be 11 kV divided by 0.612 if you are using a sine PWM technique. So this much DC voltage you require. So that means each switch is supposed to block this much voltage. So each switch is supposed to block this much voltage, and if you are keeping some factor of safety, again it's the voltage multiplied by 1.6 or something, right? So the point is that so such kind of switches are not available. So so far, so what are the device rating that are available in case of power diodes as of now? So we have 8.5 kilowatts devices are available, right? And also 9.6 kiloampere devices are available. And why we have this current rating and the voltage rating here is that so when device manufacturers are fabricating the devices, they'll keep two things in mind. So one is increase the voltage rating of the device, or else focus on the current rating of the device, right? So if they focus on the voltage rating of, or they want to maximize the voltage rating of the device, and for example, here in this case, if you see that, right, this is 8 kilovolts device, but the current rating is just 1200 amperes. So whereas, so this one, the current rating is 9600 amperes, but the voltage rate is just 1800 volts, right? So that's how they usually do that. So either they try to increase the voltage rating, or they will try to increase the current rating, right? Similarly, for IGBTs, so we have 6.5 kilowatts devices and 2.4 kiloampere devices, which are at 11 plus 1.7 kV. So these are the conventional silicon-based devices. So these are the conventional silicon-based devices. So nowadays we have the wide bandgap devices are available. Wide bandgap devices are available, like silicon carbide and the gallium nitride devices are available. So the silicon carbide IGBTs are available, and the silicon carbide MOSFETs are available. And as of now, silicon carbide based MOSFETs are more popular, so compared to the IGBTs. So with this, as of with silicon devices, we can only go for nowadays we have 6 kilowatts devices are available. But in case of silicon carbide based MOSFETs, so we have 15 kilovolts devices are also available. So direct 15 kilowatts devices are available, and the silicon carbide based IGBTs, and we have even 120 25 kilovolt devices are also available. Right. So this is silicon carbide based MOSFET, and this one is silicon carbide based IGBT. Okay. N channel IGBT is available. Right. Obviously, their cost will be much higher, so compared to the silicon based ones, because the technology is new and still mass production is supposed to happen. Right. So the point is that, so here we have the voltage and the current restrictions are there, especially voltage restrictions are there. And if you want to use these devices, let us assume if you want to use these devices for applications, right? So if you want to use some 6 kilovolts device is readily available, right? So we need to connect to cater this much voltage, like 1.6 into this much voltage. So we need to select this divided by 6.5 kilovolts. Right. So that means, so this much devices, so we need to connect in series to get the required voltage. All right. Similarly, if you want to, obviously, if the voltage rating is high, if you're directly connecting to the 11 kV grid, so it is also expect that the current rating will be higher case. So that means the power converter may be designed for 2 MVA, or somewhere between 1 to 10 or 1 to 15 MVA range, right? So that means the current rating is also very much high. So that means to increase the current rating, again we need to connect several switches in parallel, right? So that means one switch so consists of multiple series parallel connected switches. And the point is that, so every time or each time, so we need to turn on and turn off these switches simultaneously, right? So here one of the most difficult operation, one of the most complex thing in the power semiconductor is that simultaneous turning on and turning off, right? In case of series, so the we can easily do that, right? But in case of parallel, so we have to make sure that that two devices are turned on and turned off means at a time, right? For example, you are connecting two MOSFETs or IGBTs are in parallel, so we expect that, so for example it is 100 amperes, right? So we expect that 50 amperes and 50 amperes are carried simultaneously. But sometimes what happens is that if this device is turned on early when compared to the other device, so that means all the 1000 amperes will current will flow here. So that means that leads to the damage of this device, right? So you have to make sure that, so the current will be equally flown in all times, like not only transient time and also in the steady state time. So for that, so we need to do some extra precautions. So one extra precaution is that first thing is that we have to make sure that the threshold voltage of these devices are same. Like you know that every device having some threshold voltage, that is the minimum voltage that is required to turn on the device, like 2 volts, 3 volts are there. So that's supposed to be uh, equal, right? More or less equal. In other words, if it is in the same, even though if it is at the same band, same batch of production or the or right, so there will be always some tolerances in the threshold voltage. So before turning on, before selecting two or more MOSFETs that we are trying to operate in the parallel, so we have to make sure that first we need to select their threshold voltages equal, right? So that way, or else also we can connect some equalizing, some we will connect some equalizing circuits, like some small resistors we will connect to make sure that the devices will be turned on equal, means at a time, right? So these are the drawbacks. So when you are using the two-level inverter for a high power applications, right? So even though you are doing all these exercises, but still it will act as a two-level inverter only. So again, the waveform is as good as like this. The waveform is similar to this one. Again, you need to use some filters and all. And this filter is for 415 volts filter, right? Similarly, if you are using this filter for 11 kV, right? So all these one inductors and these capacitors are also rated to that much voltage, right? So that means it will also increase the filter size, cost, uh, and the weight, right? So even though whatever you are exercised, you're connecting several devices and all. So here still you're not, it is equal to two-level inverter. The performance, to improve its performance or to make the waveform close to a sinusoidal, again you need to use the filters. So therefore, if you want to directly connect some high voltage or high voltage converters or some medium voltage converter directly to the grid, so there are two options are available. So one is the multipulse converter and another one is the multi-level converters. So this multipulse converter, so you might have studied, right? So in case if you're studying the HVDC, like 6 pulse converters, 12 pulse converters, 18 pulse, 24 pulse, and the 48 pulse converters. Right. So here two converters are there. In case of 12 pulse converters, so one converter is fed from one converter is fed from one power supply, and another converter is connected from another isolated power supply, and there will be angle difference between these two converters, so which is around 30 degrees. Right. So normal thing is that for right, for 360 or for P pulse converters, so we need to provide a phase angle, so which is P. In case of 12 pulse converters, so we need to provide 30 degrees here. In case of 18 pulse converters, we need to provide 20 degrees, and 24 pulse converters, so we need to provide 15 degrees phase shift. Right. So 12 pulse converters, two converters are required. So 18 pulse, three converters are required. In case of 24 pulse, it is four converters are required. In case of HVDC applications, we use the 48 pulse converter. So under this case, so we need to use eight converters. Right. So we need to use eight converters. Thing is that, so here the outputs will be or the control will be such that, so the whatever the harmonics are produced in the 6 pulse converter, right? So when you're combining that, so that will be cancelled. So meaning is that, so this 6 pulse converter itself will produce the fifth and seventh order harmonics, like this is 6k plus or minus harmonics it will produce, right? So this is also produce 6k plus or minus 1 harmonics. So when you're combining this one, so this for example you have fifth order harmonic and seventh order harmonic will be there, and which are moving in this direction. So whereas in this converter point of view, the fifth and seventh order harmonics will be moving in this direction, and both will be cancelled out. So therefore, so if the minimum order harmonic will be here is the 11th and 13th here. So that means all fifth, seventh order harmonics are cancelled. Similarly, it is 18 pulse, the minimum order harmonic is 17, 19, like that. So that means, so this will now change it to 12k plus or minus 1. So this is 18k plus or minus 1, and this is 24k plus or minus 24k plus or minus 1. Right. So that's why in case of HVDC, so it will be 48k plus or minus 1. That means the minimum order harmonic will be 47 and 49 on the AC side, and the 48 order harmonic on the DC side. Right. So that means, so 47th order harmonics, so which value is usually very much small, the transformer leakage inductance and all, so that is sufficient to make that even suppress this 47th and 49th order harmony. Therefore, the waveform is as close as to a sinusoidal waveform. So typically, if you are using a 48 pulse converter, so theoretically you will get a THD of around 2% THD in the voltage waveform. Right. So here, in case of multipulse converters, there are certain drawbacks are there. So one of the drawback is that, so here it is, the first thing is that it requires complex transformers, right? So to produce the phase shift, so we normally use the zigzag or polygon transformers for this, or some special connection between the transformers is necessary for this. Right? So that is one of the complex thing, right? And another one is that, so they will produce 50% of the total losses, and also 40% of the space. And the another drawback is that, so when you're connecting a transformer, so if you are try if some it is connected to the converters, there is always a chance that the DC current will flow through the transformer, and that DC current will or that will induce some, in other words, it will saturate the transformer core. Right. So therefore, this is early days. So this kind of the multiples converters are used in case of facts applications, right, and the HVDC applications. Slowly, we are using the other form of applications, other form of converters for this. So next application, so which is the next thing to achieve the high power or high power and medium voltage is the multi-level inverters. Right. So as you all know that, right? For example, this is two-level inverter, and you are measuring the voltage between this A and 0 point, and this is VA0, right? And this, let us assume that this capacitor is charged to VDC. And if you imagine that this A is connect this switch, right? So this is switch is connected here, right? So that means you will get the, so you will get the VDC voltage here, and the same switch which is connected to this 0 point, that if this A is connected to 0 point here, so you will get 0 voltage, right? So meaning is that if this A is point is connected to the here one position one, so you will get VDC voltage, and if it is connected to this position 2, you will get 0 voltage between this VA0, between this voltage. All right. So that means this is producing two levels. Similarly, so now we have two DC sources are there, and there is a split between these DC sources. So top one is VDC and the bottom one is also VDC. Right? We have now three positions, 1, 2, 3. Right? So if this A is connected to 1, so from this place to this place, we are measuring voltage. Right? This is VA0. Right? So now you will get 2 VDC voltage if it is a position 1. If it is a position 2, you will get VDC voltage. If it is position 3, you will get 0 voltage. Understood? So that means you are getting 3 voltage levels. If you are increasing this one, right, some multiple levels like this, so you have one positions like 1, 2, 3, and so on, some nth position. Right? So this voltage is equal to n times VDC. Right? This is n minus 1 times VDC, and so on. Somewhere we have VDC, and you will get 0 voltage here. Right? So this is how you will get the multi-level output. Right? So here this two-level inverter. So this waveform is nowhere close to a sinusoidal waveform. So this is slightly close to a sinusoidal waveform, and this one will be a much better approximation of a sinusoidal waveform. Here you will get a more precise sinusoidal waveform. So from this, understood. This is how multi-level inverters will work. So the thing is that, so we'll split the DC into several parts, and we have different points of switches. Switch arrangements are there, so that, so we will get the required voltage level, right? And what is interesting here is that, so here each switch is not supposed to rate it for the full voltage, right? For example, this one maximum voltage from this is 2 VDC, right? But a switch will be connected between these 2 points and these 2 points, right? So that switch is supposed to block, if you connect a switch between these 2 points, the switch is supposed to block only VDC voltage, and this point, the switch is supposed to block only VDC voltage, right? Similarly, if you are connecting a switch between this point 1 and 2, right, between these two, that switch is supposed to block this much voltage only, right? So that means even though your converter is dealing with high voltages, right, but your switches need not go to or need not withstand that much voltage. So that will be, you will always get some reduced voltage, right? So that is the advantage. And another thing is that, so this waveform is almost sinusoidal waveform, right? This waveform is almost sinusoidal waveform. And another thing is that it will reduce the filter requirement. Sometimes if it is increase, you're increasing to some, for example, you make 9 steps or 10 steps waveform or 11 steps waveform. In that case, the waveform is more close to sinusoidal. The, for example, you're connecting to the grid inductance, or that is sufficient to make this even more sinusoidal. So usually the filter requirement so will be reduced, or else sometimes it will be completely eliminated. Right. So we have some advantages with the multi-level inverters. The first thing is that they can generate the high output voltages. So with matured medium power semiconductor technology, so with lower distortion, and they will reduce the EMI effect and filtering requirement. Right. So, and another in case of AC to or DC to AC applications or AC to DC applications, especially, so the input current, they will draw the input current with lower distortions, and they also reduce the common mode noise or the common mode voltage. Okay. So they will reduce the common mode voltage. So one of the main drawback with the two level inverter is the common mode voltage. So why, what is common mode voltage is that the voltage which is common in all the phases. So in case of two level inverters, so if we add all the phase voltages or some voltages, if we add all these things, you will not get a zero because all are PWM waveforms. You will get some voltage, right? So that voltage will be interact with the when depending on the applications, like if your PV application is there or some applications like motor drive application is there, so that voltage will interact with the uh, motor hardware parts, right? And that will produce some especially it will eat away the it will induce some currents between the starter and the rotor frame, right? Because there will be some parasitic capacitance edges between the starter frame and the rotor frames, between starter and the rotor frame, right? So the parasite the capacitance is, so when it is feed to a high frequencies, so here there impedance will be so very much less. So in that case, so that will huge current will flow through that, and it will generate the heat inside the machine. So that heat will be especially corrode, or it will be pollute the lubricants, or also it will pollute the ball bearings and all, right? So that is one of the drawback when in case of two level. So by using this multi-level inverters, so we can reduce the magnitude of the common mode voltages. Right? If the magnitude is reduces, so obviously the common mode current will be reduced. That will reduce the heating effect inside the machine, right? And they are fault tolerant here, so they are fault tolerant, right? And they're prone to failure, and they're less. Their cost is less relative to this, and they can operate at the lower switching frequency. So no need to go for the higher switching frequencies here, right? So one of the main advantage with the multi-level inverter is that so we can go for high voltage, or sorry, we can go for high power applications and high medium voltage applications, right? And another thing is that so we can reduce the switching losses by reducing the switching frequency, and they're fault tolerant. So for example, one switch is faulty, so we can reconfigure the inverter such that still we can work it as a at regular power, or the its rated power, or some reduced power, right? And another thing is that so we can directly integrate to the grid. And another thing is that it will the waveform, so filtering requirement is less. So there are different multi-level inverter topologies are there. So you might have aware that, right? One is the neutral point clamped converter, and then another one is the flying capacitor and the cascade bridge converter. So this neutral point clamped converter and the cascade bridge converters are very much popular compared to any other converter, right? So this flying capacitor, so which is less popular, this is especially used in the traction application, right? So now we will discuss about this first one, so which is neutral point clamp, neutral point clamp, or also known as the diode clamp here. So as we know that this is a three-level inverter, right? So three-level inverters, so typically require two DC sources, right? and you need to access the midpoint of this DC sources, right? So we have two DC sources are here, and this is the midpoint, so which is denoted as Z. Right? So to access this midpoint, right? So we have this switch arrangement is there. So between 1 and 2, so here one switch is been connected like this, and we have four switches are there in each phase. So this is S1, S2, and S3, S4. And if you observe that, so this S1 and S4 are complementary. So this one and this one are complementary here, and this one and this one are complementary here. Right? So that means this S1 and S2, S1 and S3 are complementary. These two switches are complementary, and similarly these two switches are complementary here. So S1, S3, and S2, S4 are complementary. Right. So here to access this midpoint, so we have this diodes are there, right? So these diodes are there. So that's why it is known as the diode clamped inverter. So we have clamping is there, so we are clamping this neutral point, so by using the diodes, so that's why it is known as diode clamped multi-level inverter, or also neutral point clamped. So you're clamping this neutral point, so which is known as the neutral point clamped inverter, right? So here, depending on the diodes are unidirectional devices, right? So sometimes we need to inject current to this neutral point, or sometimes you need to we need to we need to draw some point means current to this neutral point. So that means you require some bidirectional power flow here. Right? So therefore, so we have alternate arrangement or the another arrangement on the bottom side as well. Right? So depending on the current direction, whether it is from source to load or load to source, so either this diode will be conducting or this diode will be conducting. Right? So we'll discuss that slightly after 1 or 2 minutes, right? So let us assume that so this S1 and S2 are on, and you are measuring the voltage between this A and Z. Right? In other words, right? So you are measuring voltage between A and Z. So if these two switches are on, right? So that means these two switches are on. So that means the circuit will be completed like this. Right? So that means you are measuring voltage between A and Z, right? So that means your voltage is equal to E between A and Z. Right? Similarly, this top switch is off, so only this switch is on. So now this is off. So that means this is off means so this switch is on and this is off. So because S1 and S3 are complementary, right? So S1 is off means S3 is on. So now we are measuring again between A and Z, right? So that means so depending on the current direction, right? The switch is always it will be the flow will be like this, right? So for example, one current direction, so like if it is current direction is like this, right? So through this diode, so the current direction is like this, right? So through the current direction is like this, through this switch, through this diode, the current will flow, right? So that means now DZ2 will be working. That means from the power flow to the load to the source side, so it will be the direction is like this. Right. Similarly, for the other from the source to load, so in this case, the current will start from this Z point and this diode and this switch and through this load. Understood? So depending on the current direction, so either this DZ1 will conduct or this DZ2 will conduct. Right. So we have so we cannot impose any constraint on this because these are the diodes are uncontrolled devices. So we don't have control over it. So whether with DZ1 is supposed to conduct or DZ2 is supposed to conduct. Right. Understood. So now if these two are conducting, so this A is directly connected to this Z, you will get a 0 voltage. Right. So now these two switches are off, right? So now these two switches are off, like this is off and this is also off. So meaning is that, so these two bottom switches will be on. So now this A is directly connected to the negative DC bus, and this, if you measure the voltage between A and Z, you will get minus E voltage, right? So this is how you will get three levels in the output voltage. So this is how you will get three levels in the output voltage. The same way, so we can analyze the circuit by taking the voltage from here to here. Right, from B phase also between B to J, B to this Z you can analyze. Similarly for B to Z, if you're analyzing that, you will get 0 voltage minus E voltage. Between C to Z, so you will also get E voltage, 0 and minus E voltage. Right. So if you observe, these are the phase voltages, right? If you require the line voltage, so which is VAB, so which is VAZ minus VBZ, right? So if it is E voltage at some particular time, and at the same time this voltage is minus E, so you will get 2E voltage, that is maximum, right? If you are subtracting this one and this one, or this one and this one, right? Some point of time you will get that line voltages will be 2E, E, 0, minus E and minus 2E. So that means you will get 5 levels here, maximum. Right. So this is between A and B. Similarly, this is also between B and C and C and E. So that means you have phase voltages, you have 3 levels. So line voltage, maximum you will get 5 levels. Right. So that means when I are talking about the number of levels, so that means it is usually phase voltage levels only. Right. So 2-level inverter means 2 voltages, 2-level inverters, 2 voltages, right? In case of 3-level inverters, 3 levels in the output phase voltage, right? Output phase voltages. But in case of 2-level voltages, so that is slightly different. The main thing is that 2-level voltages, the 2-level inverter, the main thing is that 2-level inverter, there is no neutral point here, right? There is no neutral connection here. Right. So how you know that it is 2-level inverter? So one, we will measure the voltage between this point to this point, right? So this neutral bus, this is DC link negative, and this is A. Right? If the stop switch is on, you will get VDC voltage here, and if this bottom switch is on, you will get 0 voltage here. That means you will get VDC and 0 voltage. So that's why it is known as 2-level voltage inverter, right? So also another methods is there, like pole voltage or some fictitious voltage. So we'll split this into 2 offs. Okay, so we'll measure between these two. Okay. So here, if the stop switch is on, so you will get VDC by 2 here, and this is also VDC by 2. If this stop switch is on, so between these two, if you are measuring the voltage, if top switch is on, you will get VDC by 2. If this bottom switch is on, you will get minus VDC by 2. So that is plus VDC by 2 or minus VDC by 2. You will get 2 levels, right? Okay. The point is that in case of voltage, this 2-level voltage source inverter, there is no inverter phase voltages, right? So obviously you have load side phase voltages available. If you are connected some load here, right? So this one, if you are measuring between this is A, B, C, right? If you are measuring between these two, so that is load side phase voltages, but not inverter side phase voltages, right? So the meaning is that, so when you are saying the number of levels, so that is pole voltage levels or the phase voltage levels, right? See, usually for M level inverters, right, that means M number of levels in the phase voltage or the pole voltage. So that means you will get a maximum of 2M minus 1 levels in the line voltage. So this is phase voltage levels and this is line voltage. This is 2M minus 1 maximum. So why it is maximum is that, so here to achieve this maximum voltage like 2E in this case, so what happens is that if this inverter, this, if it is E voltage, at the same time it's supposed to be minus E voltage, right? When this happens only, it will, you will get the maximum voltage, right? If you are increasing the number of levels like 10 level or 11 level inverters, in that case, let us assume that 11 level inverter here, right? So from this formula, you're supposed to get 21 levels, right? You may not get 21 levels. So why? Because in case of 11 level inverter, the maximum voltage will be VE 4E2 minus 5E, right? If one phase you are getting 5E, in the other phase you're supposed to get minus 5E, right? So because of 120 degrees phase shift and all, you may not get the maximum voltage. So most of the times you may not get this 10E2 minus 10E. Maybe you will get 9E2 minus 9E. Understood? So meaning is that, so here the phase voltage number of levels means which is equal to the phase voltage number of levels. Right. So this is a simple neutral point converter, right? So if you want to extend this into higher levels, so that is simple. So now you have 3 levels, right? Earlier. So now if you want to increase it to 4 levels, so we need to have 3 DC sources. In case of 5 levels, you need to have 4 DC sources. So again, you need to clamp this DC neutral points, right? This is one clamping. So this is X5. So this is X between 1 and 2, between 2 and 3, and between 3 and 4. Right. So here, if you see that, right, one interesting thing here is that, or one of the main drawback with the diode clamp is that, right? So this clamping diodes, right? So this clamping diodes here, right? So this, for example, this diode is connected to this point, and at the same time, this diode is connected to this point, right? So now we'll focus on this diode D1, right? We will focus on this diode D1, so which is connected between these two, right? So that means the D1 is supposed to block. So here, this E voltage only, right? So when this switch is off, so that means it's supposed to block this E voltage, right? So whereas on the same leg, this D1, this one is there, right? This diode, okay? So which is connected between these two terminals, right? If this is on, this switch is on, this switch is on, that means this is connection is like this, right? So that means, so this diode is supposed to block this source and as well as this source. Understood? This diode is supposed to block these two sources. So that means it's supposed to block 2E voltage. So that means if you take the same rating of this D1 diode, so you need to connect two diodes in series. So that means that's why it is written as D1 dash into 2. So that means two diodes in series. So that means you have another diode, so which is connected like this. Okay. Similarly, here also you have another diode, so which is connected like this. Okay, so that means even though it's showing only one, but the rating of the diodes when you're connecting, it should be 2 times. Okay. So in case of 5 level also, so here it is written as D13, right? So that means this D13 here. So for example, this diode D13 is connected this point, and the other point is connected. So here, other point is connected. We'll disconnect this point here, right? So that means this is supposed to block the 3 voltages. So that's why it is written as D1-3. So the main drawback with the diode clamp is that it's increase in number of diodes, right? Increase in number of diodes. Even though I'm showing you the less diodes here, so in this case here, so each one this required 3 diodes and this required 3 diodes. That means 6 diodes are required per phase. So that means you required 18 diodes here. Similarly here 4, 4, 4. So that means you'll take 12 diodes here, and for 3 phase, so you require 36 diodes. Right? So usually for M level, right, you require M minus 1 time into M minus 2 number of diodes are required per phase. Right? In case of 3 phase, it will be 3 times M minus 1 into M minus 2 clamping diodes are required. You can cross check here, right? For example, 4 level inverters, so 3 into 4. So this is 3, right? And this is 2. So you will get 18 here. In case of 5 level inverter, so it is 5 into, so M minus 1, it is 4. Sorry, not 5. So 3 into M minus 1, it is 4. M minus 2, so that is 3. 3 into 2, 12 plus 36 diodes are required here. So that means M minus 1 into M minus 2 per phase is required. For 3 phase, 3 into M minus 1 into M minus 2. Right. So number of switches that required is this, like this. In case of 2 level, you require 4 switches per phase. In case of 3, 4 level, you require 6 switches per phase. In case of 8 level or 5 level, you require 8 switches per phase. So that means you require 2 into M minus 1 switches per phase. Right. So you require, so 2 into m minus 1 switches per phase. So that means for 3 phase, it will be 3 into 2 into m minus 1. So these are the main switches along with the anti-parallel diodes. And this number, so this one is for the clamping diodes. 3 into m minus 1 into m minus 2 clamping diodes are required. Right. So this is about the diode clamp multi-level inverter. So one of the main drawback with the diode clamp is that, so here the first thing is that the current flows, right? Here earlier case you have diode is there, right? So here you have so here you have these DC sources are there, and here sometimes the current will flow in this direction, or sometimes the current will flow in this direction. So here what happens is that, so here we expect that these two capacitors must be charged equally. So let us assume you have 700 volts here, and we can expect that this capacitor must be 350 volts and this capacitor must be 350 volts. Right? So then only the smooth control is possible. If these two are not same, right? So what happens is there, right? This is 353, some small variation is this will become 360 volts and this will become 340 volts, and it will not same, right? So that means positive offset is something and the negative offset is something that will also leads to the DC offset, right? So to avoid that, so we have to make sure that these two capacitors must be balanced, right? That means this neutral point is must be balanced, right? If you're measuring this voltage from here to here, so that must be off. If 700 volts, so it must be 350 volts. So automatically this other capacitor will become 350 volts. Right. If it is shifted, right? So this is known as the neutral point shifting, right? This neutral point shifting or unbalance in the neutral point. If there is unbalance in the neutral point, the positive off cycle and the negative off cycle will be different. So what we can do is that here these are the diodes are uncontrolled device, right? So we don't have the control over this charging or discharging of these two capacitors, right? So depending on the current directions, the capacitor will be charged or capacitor will be discharged, right? So therefore what we can do is that we can replace these diodes with the switches, right? So we can replace these diodes with the actual switches. So this is what it is done. So we have replaced with the switches. So this is known as the active neutral point clamp, right? Active neutral point clamp. In this way, you can actually control, or we can actually control the neutral point voltage. Right? So NPC, the main drawback is the neutral point voltage deviation. So that can be addressed by using this active neutral point clamp, right? So here the diodes are replaced with switches. But you know that, right? The clamping diodes numbers are high. For example, you are considering 5-level inverter, you require 36 diodes. So that means you need to replace these 36 diodes with 36 switches, right? When you are adding a switch, so automatically the driver circuit, everything will come, right? Driver circuit also included, right? And also for switches, diodes uncontrolled device, so no control is required when you are adding a switch. So we need to generate the firing pulse for the switch as well, right? That includes the complexity, right? So that's why, so this kind of things are not encouraged for higher levels. Maybe it is good option for a 3-level case, right? Maybe it's a good option for 3-level case. If you're increasing it to 4-level case, you need to add 18 switches. In case of 5-level, you need to add 36 switches, right? So that's why it is in case of 3-level, so maybe you can add 6 switches here. So that may be relatively less cost effective when compared to this, right? So we have other options are there, like so we have one more option is there, right? Okay. So this is another one, so which is derived from the neutral point clamp, but this is popularly known as the T-type converter, right? So this one is very much popular. So nowadays, so this one is very much popular nowadays for the 3-level application, right? 3-level application. This is very popular. The first thing is that the circuit topology is similar, right? It will be with some reduced number of switches. The point is that we have one switch will be here and another switch will be here, right? In phase layer, and this this pair of switches, this one is there, right? So this is the bidirectional switch. So this one is bidirectional switch, meaning is that so it will allow the current in both directions, right? And it will also block the voltage in both direction. It will allow the current in both direction, and it will allow the current, or it will block the voltage in both direction. Right? In other words, it's a four quadrant switch, right? So whereas this one, right, it will block the voltage in one direction, it will block the voltage in one direction, but it will allow the current in both direction. So in case of switch here, diode here, both direction current flow, but it will block only positive voltage, right? So whereas, so this one will allow the current in both direction. For example, if the switch is conducting here and through this one or through this, right, and it can block the voltage in both direction, right? It can block the voltage in both positive and the negative direction. So it is known as the four quadrant switch. All right. Clear? So here, by using this four quadrant switch, so which is connected to the neutral point, this A between this neutral, all these points are same, just all are same points only. We are accessing same points. So between B and neutral point, so between C and neutral point.
Captain
Right.
DSR,
Yes, sir.
if you want to have a break, means you can take for 5 minutes.
Okay, sir. We will take some 5 minutes break, sir.
Yeah.
Okay. You have any questions? You have any questions so far? So there is a question on the third part. So one is the for the prospect of the grid tied inverter applications. So which is better, voltage source inverter or a multi-level inverter? So the answer is obviously voltage source inverter is better, right? The thing is that so two-level inverter or the multi-level inverter. So that all depends on the voltage rating you are considering. So for example, you are considering for a low voltage case like 415 volts or something, right? So two-level inverter is sufficient. So whereas we are dealing with some voltage of 3.3 kV, 2.3 kV grid, or some 6.6 kV or 11 kV grid. So in that case, the best thing is that so you need to go for the multi-level inverter.
Asina sir?
So we'll start, sir.
Yeah, yeah, sir.
So we are discussing the alternatives for the neutral point clamp. So one alternative is the active neutral point clamp. So another alternative is this T-type converter. So as we discussed, this T-type converter is more popular, especially for this applications of EV, right? So this we have now T-type chargers are available, charging circuits, solid-state transformers, solid-state transformer applications, and for the grid connected applications. So this T-type converter is more popular, right? So the operation is like this. Okay, so these two switches are complementary, right? So if we assume that these two switches, the switch S1, this one, the top switch is on, we are measuring the voltage between this A and 0. Okay? So you will get this voltage upper one. Similarly, so when the bottom switch is on, right, when this bottom switch is on, if we measure the voltage between this A and G, so you will get this voltage so with negative sign, right? So if we imagine this VDC1, VDC2, both are same, in that case, so you will get the plus VDC by 2, so for example, this is VDC, so this is also as imagine it's VDC, you will get minus VDC, right? So this one is for top switch is on, so this is when the bottom switch S3 is on, right? Similarly, if you want zero voltage level, right? So if you want zero voltage level, this switch and this switch between zero voltage is required, right? So that means this switch is supposed to turn on, right? So this switch is supposed to turn on, right? So if you turn on this switch, so you will get this zero voltage here. So right. So here you are getting the three voltage levels. So VDC voltage, zero voltage, or minus VDC voltage. So again, so that's why it is known as a three level inverter. So this is in the shape of T shape, right? This is a T shape, right? So that's why it is known as a T type inverter. So there are some advantages. So with this, the first thing is that so you require less number of switches. You require less number of switches. And another thing is that so even though these two switches are same, two switches are if you observe that these two switches are connected in anti-series connection, right? So you require one gate driver circuit only. So for this circuit, you require one gate driver circuit only. So here this one is emitter here. So this is also emitter here. So this is a common emitter configuration. So this is a common emitter configuration. You know that, right? Gate pulse is connected between the gate and the emitter, right? So gate and the emitter connection in case of IGBT. In case of MOSFET, it is connected between the gate and the source pin, right? So it's a common source configuration. In case of MOSFET, it is a common emitter configuration in case of the IGBTs. So therefore, if these emitters and gates are common, you require only one gate driver circuit is sufficient. Right? You require one gate driver circuit is sufficient. It is something else like common collector configuration or something, right? Common collector configuration. In that case, you require two gate driver circuits, so which must be isolated each other. Okay. So here, even though the two switches are there, so you require only one gate driver circuit. Right? And another thing is that so this voltage, right? So it's supposed to block this voltage by two switches. So that means theoretically, so this device is supposed to block VDC by 2 voltage only. Right? This device is supposed to block VDC by 2 voltage. And another thing or other one of the main thing we need to consider these main switches. So this switch and this switch, right? For example, this switch is on, right? This switch is off like this. Okay, so this is off. So in this case, so this is supposed to block these two DC source voltage, right? So that means this switch is supposed to block 2 VDC. So this is also supposed to block 2 VDC, right? So this single switch is supposed, this entire switch is supposed to block VDC. Understood. So that means, so when compared to the diode clamp, so here the switch requirement is less number of switches is required, but only drawback is that the main switches is supposed to be twice the rated. In other words, it is equal to two switches. Okay. So that is one of the drawback. But the good thing is that, so compared for 3-level case, the cost wise there will be huge difference here, and we have lower conduction losses when compared to the diode clamp. So that's why. So this is very popular, especially in the EV drivetrain, electric vehicle chargers. We have chargers are available for 350 kilowatt chargers or 250 kilowatt chargers are there at high power charging. So most of the high power chargings they prefer this T-type converter. So we have the dual active bridge converter will be there. So dual active bridge DC-DC converter. So one side we have, this is usually based on the T-type converters. Like similarly for solid state applications, like if you are connecting to the 11 kV grid solid state transformer 11 kV to 400 kV or some intermediate 3.3 kV voltage. So we are using this three level T-type inverter as for the DC to AC conversion. Right. So for grid integration applications, integrating with the 11 kV or from 3.3 kV or 6.6 kV applications, also we are preferring this T-type topology. Right. So most of the work or almost even the direct modules are also available for the different manufacturers like the Wolfspeed, ST Microelectronics or the Infineon devices. So direct three-phase module is available. So that means module means this entire phase leg in one module, or else this A phase leg, B phase leg, or else entire this three-phase inverter in one module. So that is also available like this. So this kind of modules, this is the this is a two-level inverter module. This is off bridge, and these are the discrete devices. So this entire modules are nowadays available for the one phase leg or the complete three-phase inverter, right? So you can see here on the bottom. So this circuit is there, right? So this is for two-level inverter. Similarly, we have T-type three-phase direct three-phase inverters are available, or else a direct or else one phase modules are available, right? So that means you can imagine that much popular it is nowadays, right? So next one is this cascade edge bridge inverter. So this is also very popular for applications like grid connected inverters and the PV integration and the energy storage systems. This is especially important for the STATCOM applications, right? For the PV integration, for integrating a large PV farm, energy storage systems, right? And for the large electric vehicles, right? And for other grid connected applications or anything like. So this is another important thing. So this is known as the cascade edge bridge inverter. So here this is one H bridge. So you're aware of this. This is another H bridge. So here these two H bridges are connected in cascade. That means the output of one H bridge is connected like this, right? So this is forming one phase, right? That means outputs are connected together, right? So this is B phase, and this is A phase, B phase, and C phase, and this point is the neutral, right? So here each H bridge, you know that, right? This entire module will produce three voltage levels like E voltage 0 minus E. So this is also produce E voltage 0 minus E. So when you're combining from this point to this point, right? So when you're combining to this point, so let us assume this is producing E voltage at the same time. So this is also producing E voltage. So that means the total voltage is 2E. Similar at the same time, it will produce 0 voltage. So that is E voltage. So both are producing 0 voltage, that is 0. In other words, 0 can be obtained in different manners. For example, this is you are getting minus E here, plus E here, and you are measuring between this point to this point, you will get 0 voltage, right? Similarly, with this is plus E and this is minus E, that is also you will get 0 voltage. Similarly, minus 2E voltage and minus E voltage and minus 2E voltage also you obtain. Understood. So that means from here to here, you are measuring between A and A to N, this point. So you will get 5 voltage levels. Similarly, between B to N, you will get 5 voltage levels, and between C to N, also you will get 5 voltage levels. Right. So this is the phase voltage levels, and if you go for the line voltage levels, so that will be somewhere between 4E to minus 4E, and you will get 9 levels. you will get 9 levels in the line voltage. Understood? Okay. So if you have two H bridges in cascade, right? You will two H bridges in cascade. So it will be become 5 level. So that means 2H plus 1. So H is the number of H bridges in cascade. So H is the number of H bridges in cascade. Okay. So this is equal to level number M in the phase voltage. Right? So this is phase voltage levels. Similarly, here 3 H bridges are there. So you will get 7 levels. Right? And 4 H bridges are there, you will get 9 levels. The level number is always odd number. The level number is always odd number. So here one important thing is that so it will be symmetrical or it will be a symmetrical case. In case of symmetrical, so this is E voltage, so this is also E voltage, so that will become a symmetrical H bridge or cascade H bridge. If this is of a different voltage rating like 2E voltage or this is E voltage and this is 2E voltage, so this is become asymmetrical. So with asymmetrical, you can increase the number of levels, right? Like it is E0 minus E, and this will become 2E0 minus 2E, right? So combining these two, if you measure voltage between VA and N, so this will become 3E2 minus 3E, so that will be 7 levels. Right? So that will be 7 levels. Understood? Similarly, we have 3E also, so now it will be 3E. So if it is 3E like this, and now it will become 3E2 minus 3E. So that means the total number will be equal to 4E2 minus 4E. So you are getting 9 levels. Right. So depending on the voltage ratio, we can do that. But there is a limit for that. So you cannot go for voltages like 4E and so on. So let us assume that you have chosen something like that E voltage and 4E voltage. Right. E voltage and 4E voltage. So in this case, it is E0 minus E. So this will produce 4E0 minus 4E. Right. So you cannot obtain all number of levels. For example, you can get 5E levels by operating this as E, this as 4E. You can get the 5 level, 5E. Right. If you want 3E, right? So this will operate as minus E. So this is 4E. You will get you will get sorry. If you want 4E, so this is 0 voltage and this is 4E voltage. You will get 4E voltage. And if you made this minus E, right? You will get 3E voltage. So if you want 2E voltage, right? So with this combination, you cannot get 2E voltage, right? With this combination, you cannot get 2E voltage. So that means this 2E voltage is absent. E voltage you can get, 0 you can get, minus E you can get, minus 2E, again you cannot get, right? So that means voltage directly jumps from 3E to E. So this kind of things you need to avoid. Right. So there is a limit for this. You cannot increase or you cannot have a random number of H bridges. And another thing is that it is 4E, right? So this must be 4E. So this must be 4E for a symmetrical case. Or if it is 3E, it must be 3E. So here they are in some relation, right? So these H bridges are in some relations, like we have 1 is to 2 is to 3 relation, and also 1 to the power of 0, 2 to the power of 0, or 3 to the power of 0 relation, or else we have the these are in the arithmetic progression or in the geometric progression, or 2 to the power of 0, 2 to the power of 1, 2 square, and 2 cube, and so on. Similarly, 3 to the power of 0, 3 to the power of 1, 3 square, and 3 cube, and so on. So these are the valid ratios, like it is 1 is to 2 is to 3, another one is 1 is to 2 is to 4 is to, and something 1 is to 3 is to 9 is to 27, and so on, like this, right? So these ratios only, for example, if you select these things, right? So with this you can get 81 levels, right? So with this you can get 81 levels. So with 4 H bridges you can get 81 levels. But the drawback is that, for example, you are selecting this is 27E, so all the switches is supposed to get supposed to rated for 27E voltage, right? So that is the one drawback. And another thing is that there are methods are there. For example, so all are not operating in the PW mode. So here the highest voltage, for example, this 27E voltage is there. So this will operate in the fundamental frequency mode. So remaining this one voltage levels will be operated the PWM mode, okay, like this. So here, so this one is operating in PWM mode, and this one, so highest voltage level, this is operating at the fundamental, and this is the output voltage. Okay. So this is the advantage with this one. So we can implement asymmetric switching. Okay. Understood. So this is the advantage with the asymmetric operation, but mostly asymmetric is not preferred because so we need to balance the capacitors in some applications. We need to balance the capacitors and all. So therefore, most of the cases, so this kind of asymmetry is not encouraged. For example, your 2E is there, right? So we need to balance this capacitors every time, or we need to maintain the voltage ratio every time. So that is not something easy task. Right? So now the point is that so how these voltage sources are feed. So these are isolated voltage sources. So you require isolated voltage source. So this one vary depending on your application, right? For example, you are using energy storage system. So each one is a one battery here, all are batteries here, all are batteries or supercapacitors or some energy storage device. So in case of energy storage system application, in case of PV, so here, so each one is fed from a PV, right? We have some PV will be there, right? With PV with MPPT, and this is connected like this. So this is also you have another PV, so which is connected like this MPPT, like this, right? So if it is something like the electric vehicle application, in this case, so all are batteries only, right? All these sources are all these are batteries. Okay. So we have battery pack will be there, right? Instead of if it is two level, one battery pack is sufficient. Whereas in case if you are connected to a multi-level inverter like this, so you need to split the battery pack into several parts. So here, in case of you are using the same converter, the battery pack now we are split it into 6 parts, right? So in case of applications like StatCom, right, or the DStatCom applications or the active power filter applications, that are active power filter applications. So in this case, so these will be capacitors. Okay. So here have the capacitors here. So this capacitors we must be maintain some voltage across this capacitor. Okay. Obviously, we need to maintain some voltage across this capacitor. So we need to include extra control to maintain these capacitors voltages in a balanced thing. Right. Understood. In case of application like motor drive, so motor drive applications, right? So in this case, not EV motor, some regular motor. So in that case, we need to draw the real power from this, right? So we need to feed this. For example, we are connecting a motor here of high power motor, maybe 1 megawatt or 2 megawatt motors. So this kind of power converters are preferred. So if you want to feed this one, so here you need to design the input power here, right? So this power must be from grid. So for that, you normally require a multipulse converter here. Multipulse converter. So for this case, you require a 36 pulse converter. Right? 36 pulse, you know that, right? It is 6 pulses, 6 converters are connected like this. So there are 6 converters are there. Okay. So you have some transformer arrangement. So this gives you one supply, this gives you one supply, this gives you like this. Okay. So this will feed this DC one. So this will feed this DC one like this. So each one we need to feed separately. This is for real power transfer applications, right? Where we need a motor drive or something, right? Right. So the circuit will be something like this. So this is in case of a motor drive. Okay. So these extra things you require to maintain the real power transfer. So in case of EV charging, obviously batteries will be there. So this setup is not required. Right. In case of energy storage system also, so this motor, instead of motor we have a grid here, right? So depending on the applications, so what kind of DC sources that require, it will change. Right. So here, that's why one of the major drawback with CHB is that in case of motor drive, especially for real power transfer applications, you need to have, so this must setup, right? So again, for front end, so you require these setups. Right. So that's why it is not encouraged for low power applications unless you have very large power applications for 2 megawatt, 20 megawatt. For example, steel mills, the motor capacity itself is somewhere between 550 megawatt or 100 megawatt motor will be there. In case of lift irrigation projects also, so we have the motor capacity which is huge, somewhere between 20 to 50 megawatt motor is required. Like lift irrigation projects or steel mills. So under this case, so this kind of converters we need to use. Alright, understood. So here one main advantage with this one is that so its control is simple, or the arranging this is simple. Okay, that is the thing. So another one is this flying capacitor multi-level inverter. So compared to these two, so this is very less common, but we have dominant applications in this one is the uh, traction drives. So here the multi-level output can be obtained by these pre-charged capacitors. All these are pre-charged capacitors. So this is charged to E level, so this is 2E level, and this is charged to 3E level. All right. So here, so this switch, so this S1 and S4, this S1 are complementary. So here these two switches are complementary. These are complementary like this, right? So if you are means if you are this all are on, right? If all are on, you will get this 4V voltage, and for example, these three are on, you will get this 3E voltage, and this here two are on, you will get 2E voltage and E voltage likewise. It is operated. Right? So here, this is very much not very popular when compared to others, right? But you can obtain. We have some applications like traction drives. In case of traction, we need to have a frequent regeneration is there, right? So regeneration. So the meaning is that the power we need to feed it to the grid, right? So here, for example, train is moving, or for example, train is supposed to coasting or something at the decelerating, or from the gradient is means we have some down gradient is there, right? Due to that also, so we need to send the power to the from the whatever the power is stored, or the kinetic energy stores in wheels, right? The kinetic energy stored in the wheels, so we can actually feedback to the supply, or feedback to the grid side. Right. So for that, what we normally do is that the whatever the stored energy is there, that from stored energy it will move to the crankshaft. From the crankshaft, it will move to the engine or the motor. So from the motor, it is moved to the inverter. From the inverter, it is moved to the grid side, or some super capacitors or some energy storage system. It will move. Sometimes it will feed to the grid, or sometimes whatever internal purposes like for turning on lights, or lights for lights, or charging the inside batteries of the train, so that is used. So most of the times that is used to serve instead of feeding to the grid. So usually they whatever that local loads are there, right, for inside the train, so that we for that purpose it is used, right. Right. Because these capacitors are there, right? Capacitor will quickly take the energy, and from this capacitor it will quickly store that energy. And see here, in case of kinetic energy stored in the vehicles or wheels, right, it is half mv square, right? So when the wheel velocity is reduced by half, the kinetic energy stored will be only 25%, so 75% will be dissipated. So we must act quickly to capture that energy. So one of the quick way to capture that energy is the supercapacitors or these capacitors. So first we store in the capacitors, so later on we will feed to the main battery, or else we feed to the grid. Right. So this is the comparison of different components requirement for this different multi-level inverters. So as we discussed, so this one is CHB as we discussed. So it requires less number of components when compared to other, right? So everyone has their own drawbacks. For example, diode clamp having a one drawback of clamping diodes, right? In case of flying capacitors, so we need to pre-charge those capacitors. And in case of CHB, we need to arrange the isolated DC sources. One of the important thing is the modularity. Okay, so CHB is less modular. So cascade H bridge is cascade with modularity is very high when compared to that. So that is easily scalable. We can increase the number of levels. If you want to increase one more H bridge, you can add in all phases. So that will increase the capacity, right? And applications, as we discussed, for low power applications like low voltage applications, this diode clamp is a good option, right? So whereas for traction applications, this flying capacitor is used. In case of applications like the fax, custom power devices, high power speed drives, right? And photovoltaic carry PV conversion, UPS and power supplies, and this MRI scanning are for the X-ray machines. So this kind of CHP is preferred, right? So cost will be, so here depending on the CHP, if it is you are using it for a motor drive, that cost will be extremely high. In case you are using it for a motor drive, it is very high. For other applications like STATCOM or for the energy storage system, their application their cost will be relatively less. Right. So these are some of the merits of this, or some of the comparison of these multi-level inverters. The common drawback of this multi-level inverters is the number of device count. Right, as you are increasing the number of levels, the device count will be gradually increasing. Right? So therefore, we come up with other solutions, so which are popular from the last 10 years, so which is known as the reduced switch count multi-level inverters. So their objective is to reduce the number of switch counts or increase the power density of the converter, right? So there are some objectives are there. So one is the reduction in the switch count, so increase the device blocking voltage or the modular structure, and make the converter as fault tolerant as popular, right? And voltage balancing, some of the drawbacks are voltage balancing to nature of the DC link, and requirement of bidirectional switches, switching and conduction losses minimization. So these are the main factors so that are influencing in developing some new converter topologies. One is the reducing, the main one is reducing the device count, in other words, uh, using balancing or the self-balancing ability of the converter and reducing the switching losses. So this is the main motto of inventing some new inverter topologies, right? So these can be classified in different manners, like symmetrical and asymmetrical converters, or some H-bridge based converters. Rather than this, I will show you some topologies. Right? So one of some of the commonly used converter topologies, especially for grid-connected applications or some other applications, right? So this one is the MLDCL, multi-level DC link, SSPS, series switched parallel sources, series connected sources, and reverse voltage topologies, modular MLM topologies, and this reverse current volt. These are some separate level and polarity generator based methods, right? If you see that, right, so all are consists of some H bridges, right? So all these are consists of some H bridges, right? So all are consists of some H bridges. So here the circuit is divided into two parts. So this part, right, this part produces the number of levels, right? On the left hand side produces the number of levels, and right hand side, so which will convert or which will divide this into positive half cycle and the negative half cycle. So that's why it is known as the separate level and polarity generators. So we have another one is the T-type topologies. This one we discussed. So this is one T-type inverter for single phase, right? And this is cascade connection of T-type inverters. So this is what we discussed already. So this is the T-type off-bridge converter. This one, right? So these are T-type converters. So another one is the ladder-based structures. So this look like a ladder-based structure. We can move like this, like this, like this. So to obtain the number of devices, for example, you can like this, you can move like this. So these are the ladder-based structures. Right. So next one is the level doubling networks. So we have two level inverter will be there here, and we have another cascade edge bridge inverter is there. So this is two level, and this is cascade edge bridge inverter. So we are coupled these two networks. Right. So next one is the hexagonal switch cell based. So we know that, right? HSC is there, right? So this one is HSC, and we are adding some more switches to that. So to form a hexagonal switch cell like this. And this one is another important one. So this is switched capacitor topologies. So we have only single DC source. So we have single DC source. With single DC source, we can obtain multiple number of levels, right? Single DC source. So we can increase the number of levels. Okay. So this one is also, this is HSC unit, so hexagonal switch unit. So we, H bridge, right? So we are added these two additional switches, right? And we are added another source here, right? So H bridge will form three voltage levels. So which will, this gives you five voltage levels, right? These are transformer based solutions. So we are using the transformers to obtain this. Right. So we'll discuss one by one quickly. So this is what we discussed is the multi-level DC link converter. So MLDCL, multi-level DC link converter. Right. So as we discussed, this is two parts. This one is the polarity generator part, and this one is the level generation part. Right. So first we focus on the level generation part. Right. So this one is one basic unit here. So for this case, there are 3 units are connected. Right. So 3 units are connected here. So the operation is fairly simple. So this is one chopper cell or off-bridge cell. So the circuit is something like this. Okay. So we have switch here and we have like this. This is the thing. Both are same. So here you are measuring the voltage between these 2 points. Right. So you are measuring the voltage between 2 points. This is VDC. If this switch is on, you will get VDC voltage. Right. If this switch is on, you will get 0 voltage. Right. So here in this case, for example, the switch S1 is on, S2 is on, and S3 is on. The path will be like this. So it will be start from like this source, this switch is on, this switch is on, like this. Right? So that means if you are measuring the voltage between these 2 points, right? So that means we assume that VDC1, VDC2, and VDC3, which is equal to VDC, all are same. So that means you are measuring this voltage from here to here, you will get 3 VDC. Correct? So you will get 3 VDC. So imagine if S1, S2, and S3 are on. Similarly, for example, you require 2 VDC only, so you can bypass any of this cell, right? For example, you will start like this, and I bypass this middle one, and I bypass this middle one like this, right? So now the current will be flow like this. So now you will get 2 VDC voltage. And if you bypass, we require only 1 VDC. So you can bypass this. You can only access the third source. Right? So that means you can get 3 VDC voltage, 2 VDC voltage, and VDC voltage. Even also you can get 0 voltage. If you want 0 voltage, so you can directly turn on this. You can bypass all, you will get 0 voltage. Understood? So that means with this, you are getting 0 VDC, 2 VDC, and 3 VDC are generated. Right? Alright. So here, these are the levels you are generated here. Right? So here on the other side, so you have an H bridge. So what is the use of H bridge? For example, this switch is on, these two switches are on, you will get a positive off cycle, and these two switches are on, you will get a negative off cycle. Right? Depends. For example, this one gives you the positive off cycle, and these two switches will give you the negative off cycle in this case. Right. So that means basic operation. HPC normally requires some DC source. Right? If you give a single DC source, you will generate this positive off cycle and the negative off cycle. Instead of a single value of DC source, if you are feeding this multiple values, right? So what happens is that you will get a stepped waveform like this. So that means you will get a waveform like this. This is positive off cycle, and this will be the negative off cycle like this. Understood? Okay. So now you are getting a multi-level output, something like this. So this is the generated by the level generator. So this is the one that is generated after the polarity generator. Okay. So this is the output of this one, and this is the output of this one. So in this way, you can increase the number of levels, or in other words, you can operate the converter. Understood? So here when you compare to this edge bridge or cascade edge bridge, so you require less number of switches, but the drawback is that the switches must be rated for 3 VDC voltage in this case. Right? All these 3 voltage sources you need to block from these switches, and this H bridge so obviously operate at the fundamental frequency, right? So here If this is getting means, so these two switches are on, right? So here for this voltage, so here you need to turn on these two switches. So these switches, the switches in the H bridge are operated at the fundamental frequency, but they are supposed to block the full DC link voltage. This DC link voltage they are supposed to block, right? You require less number of switches, so when compared to the cascade H bridge. Understood? So now we can also increase the number of levels. For example, you can insert, this is 3 units here connected, right? So you can connect one more unit, you can connect one more unit like this. So you can also increase the number of levels. So this is about the multi-level DC link. So similarly, we have other topologies. So this is switched series, parallel connected sources. This is another one. So this portion is same. The operation of this one is same. So only thing it will change. Right. For example, here, if you want to connect these 3 on series, you can connect like this. Okay. If you turn on switches S2 and S5, you will get this voltage. All right. So you can bypass 3 voltage. If you can bypass any switch like this. If you want to bypass, you can bypass the first source. Right. You can also bypass the second source. You can bypass like this. 2 sources will bypass. Understood? Yeah. So this is one of the advantage, or this one, right? And another thing is that we can connect. We normally have single DC source here, so we can replace this with capacitors. So now we can replace with capacitor here. Replace with capacitor. Now you have only one DC source. With one DC source, you can use, right? So to charge this capacitor, what we can do is that if you turn on the switch S1, S5, right? So all these capacitor negative plates are connected here, right? So capacitor negative plates are connected. Okay. Similarly, if you turn on the switch S3 and S6, positive plates of the capacitors are connected. Right. So that means the equivalent circuit under this case is like this. Okay. So now all the capacitor charged to VDC, VDC, VDC. If you turn on the switch S1, S4, if you turn on S1, S4, so this is the effect of S1, S4. If you turn on these 2 switches, so this is S3, S6. Understood? So that means with single DC source, so you are boosting the voltage, right? So that means with one VDC voltage, so you are boosted to 3 VDC voltage, right? So obviously, so you need to maintain the balance across this voltage, right? Every time, so we have to supposed to maintain, so VDC voltage here. So here also we need to voltage. This is just capacitor. We need to maintain the voltage, DC voltage. So every time, so we operate the switch at some point of time, so the capacitor voltage will be recovered, right? The capacitor voltage will be recovered, right? So with single DC source, so we can increase the number of levels, right? Similarly, there are other topologies are there. So this is reverse voltage. This one, this is also same. So this entire thing is produces the number of levels. So this will produce the uh, polarities. So there are multiple topologies are there. At least 10 to 15 topologies are there in the literature. All are based on this only. Right? So this is another one. Okay. So this is another one. So this is everything has their own advantages and drawbacks. For example, so in this, what is the main disadvantage is that, right? For this switch, so this switch is that this is switch, so it should be blocked these 3 voltages, right? So this should block. This is blocked 3 VDC voltage. This is VDC voltage, and this will block VDC voltage. So every switch has their own disadvantages here, right? So this is also another one multi-level module. So if you want to increase this one, so we can directly operate like this, right? Like if you turn on only switch S1, similarly you can operate like this. You can operate like this, like this. So everything, if you want to bypass, you can bypass this one. Right? In fact, the switch is not very much required here. The switch is only to obtain the 0 voltage level, but we can remove this switch. If you want 0 voltage, you can turn on these 2 switches, or you can turn on these 2 switches. That gives you the 0 voltage. Right. So next thing is the T-type topologies. So this is already we discussed. Right? So this is single phase or T-type topology. So this is a single phase T-type topology. So this entire thing is a single phase. So this is a cascade connection of T-type topology. Okay, if you want, you can connect one more here, like this. Okay. So each one will producing 5 levels. So this is producing 5 levels here. This is also producing 5 levels. So this is one of the emerging topologies for the grid connected applications. Right. So this operation is similar to the three-phase that is already discussed. Right. So these things also we discussed. Right. So now the point is that if you want to increase the steep height to the higher levels, so earlier we have only this one is there, right? Another thing is that there are two ways to increase the number of levels. So one is this, one is the splitting this one. So now earlier we have two DC sources. So now we have three DC sources. So one bidirectional switch between 1 and 2, and another bidirectional between 2 and 3. Right? That is one way to increase the number of levels. So other way is that simplest way is the cascading, right? So this is one module here and this is another module. So we are cascaded this. So this will produce 5 levels and this produces 5 levels. So combining this, it produces the 9 levels, right? So combining this will produce the 9 level voltage. So every topologies, there are two ways to increase the number of levels. The first way is the cascading. Second way is in one unit increase the number of DC sources. Okay. So this thing we already discussed. Right. So this is another way, or so before that you need to discuss this one. Right. So this is known as the hexagonal switch cell. This is just an extension of a H bridge. So this is an extension of a H bridge. If you see that this, if this is absent, if these two switches are absent, right? So this is just an H bridge, right? So by adding these two switches and one DC source in the opposite direction, so we can increase this one to 5 levels, right? So for example, the idea is to bring these two in series, right? So bring these two in series. Somehow we need to bring this like this connection we are supposed to do across the load terminals, right? So for example, you're moving this one like this, right? So here, so this switch and through, so this DC source, right? So we can connect like this, right? So this way, so we can bring these. So this is this one is positive, negative to positive, and this is also negative to positive. So this way you can connect this VDC1 and this VDC2 in series. All right. So for negative voltage levels, so here we can use this one. We can connect like this. For example, you can also connect like this. This switch is there, right? So we can also use this upper one or this upper switch for this purpose. Like this, you can use this one. So this will gives you so VDC1 voltage. Similarly, if you are using this one, right, this one, so this will gives you another DC voltage. So that means all possibilities of so we can obtain. If we assume these two are same, so we can get 2E voltage or 2 VDC voltage. VDC is 0 minus VDC and minus 2 VDC voltages, right? So here two HSC units, so which are connected in cascade. So two HSC units, so we can connect it in cascade. Okay. So there are other alternative arrangements like this. So we have one side we have split on this one DC source, right? So here the fixed one. So other side we have split on this one. This is just a mixing of the HSC and the T type, right? So this one is HSC unit, and other side we have the T type. So as you know that a lot of all these multi-level arrangements, there are mix of the uh, some of the existing ones like H bridge. We add one more circuit or one more switches or one more DC source, or we split this DC link somehow or some other way, so we can achieve the number of levels. Right. For example, this one is a T type and this one is a HSC. Right. So one side we have split here, so we can increase here like this, right? And also here we can increase this one, right? And another thing is that this is another one that is produced by another one. This is T type here, and this is T type here. So in between you have a HSC. All are like this only, right? If here something is there, so we'll add some other, right? So that you can increase the number of levels. So these are another one. So this is switched DC sources, right? Here the DC sources are connected in between, right? So we can navigate like this. For example, you can navigate like this from this DC source to this one, from this one to this one. Like you can navigate, no, not this. So from here to here, like this you can navigate, right? So you can also bypass certain switches, or you can bypass this one like this. You can increase the number of levels, right? So this one is a slightly interesting one, so which is known as the switched capacitor multi-level units. As we discussed, you have only one capacitor or one DC source is there, that is a fixed DC source is there. So rest of things are capacitors, right? So this is one basic unit here. So let us assume this is VDC voltage here, and we have one capacitor is there. So your objective is to charge this capacitor, right? Charge this capacitor by parallelly or bringing parallelly to this DC source, right? So for this, what we can do is that this is VDC voltage. So if we turn on the switch P, right? If you turn on the switch P, what happens is that this DC source and this capacitor both will be in series, right? We have one DC source will be there, and in between you have diode, which will be forward biased, and here the switch is there, right? So this P switch is on, right? So now this capacitor charged to VDC. So now this capacitor charged to EGT, VDC as when you turn on the switch P, right? Right. So when you turn on the switch S, right? So during the levels, if you want to require, you'll turn on the switch S, right? So here now the path will be something like this. So here it will be from here to this case, right? So now you understood, right, why this diode is required, just to prevent the capacitor from discharging or prevent the short circuit or discharging through the thing. So you need this diode, right? So now whenever you want to discharge this one, so you can get these levels, right? So now the voltage will be 2 VDC. So one is the capacitor and another one is the DC source. Similarly, you can also bypass this one. If you turn on only this P, so you will get like this, right? Also, you can, for example, if nothing is turned on here, if these two are absent, so in that case, it will be VDC. So that means you can get VDC voltage or 2 VDC voltage and VDC voltage with this. So that means we have single DC source is there like this. If you want to extend this one, for example, you have three capacitors are connected here instead of single. If you turn on this P1, P2, and P3, so all this C1, C2, C3 will be in parallel and again in parallel to this fixed DC source. So now it is charged to VDC, VDC, and VDC. So whenever the load is connected, so depending on, we can turn on this S1, S2, and S3. So with that, so we can actually increase the number of levels, right? So the thing is that we are getting only unipolar levels. So therefore, to make it bipolar, you require this H bridge, right? So you need this H bridge to make this bipolar. Understood? So these are known as the switched capacitor multi-level inverter. There will be another thing is that there will be voltage gain will be there, right? For example, this case, the gain of the converter, like usually the gain will be associated with the DC-DC converters, like high gain converters or the quadruple gain converters. So here also we can define the gain of the converter. For example, this is VDC, right? We have one DC source and the output voltage may be 1, 2, 3, 4 times, right? It is 4E, it will vary between 4E to minus 4E, right? So that means the gain of the converter will be 4, right? So the gain of the converter is 4. Understood? So with single DC source, so you can actually increase the number of levels. So there are many other topologies are there like this. So this is also switched capacitor topologies. Like you have one DC source is there. So multiple capacitor units are there. For example, this one, maybe the gain will be 3 times. So maybe this gain will be some other times, right? Understood. So which are known as the switched capacitor multi-level topologies. We have one DC source. We can actually increase the number of levels. But the drawback is that so we need to maintain the balance, right? So these capacitors is supposed to be balanced properly. So then only you will get the actual things, right? So we have other topologies are there. So these are in the literature, but like this entire thing will produce the how much it is 13 level voltage, and this will produce the 70 level voltage, right? But these things are not very much things, right? Because the main drawback is that so these are not modular, right? These are not modular. For example, we don't know whether how to balance these capacitors or the power, for example, this is 2 VDC voltage, 2 VDC voltage, and this is VDC and VDC, right? So maintaining these voltages is also difficult thing, and we need to make sure that the power is equally distributed, right? So meaning is that the power distributed by this VDC and this VDC should be same, right? And this 2 VDC and 2 VDC that also same, and the thing is equal to it must be double, right? So it must be same, and at the same time it should be double, right? The power flow or whatever the power distribution among these DC sources, it should be equal. So a lot of topologies are there, right? So all if you understand one or two topologies, so rest of the topologies we can easily understand, right? So we'll stop here in the afternoon section. We will discuss some more things on the PWM schemes, and we will see how to integrate these converter or some one converter to the grid. Right. So you have any questions? You have any questions?
Please, sir, can you check this chat box, sir?
Yeah. So are there any specific challenges faced by power electronic converters enabling grid TV and GPU topologies to support them? So inherently, it is expected that all converters will support the bidirectional power flow. Right? So all these converters will support the bidirectional power flow. Right? So as it supports the bidirectional power flow, so obviously the grid to vehicle or vehicle to grid or vehicle to load. So all these things are possible. So every converter, what we discussed, like diode clamp, cascade edge bridge, or the T-type or the MLDCL, all are bidirectional only. And another good thing is that if you want some bidirectional flow, so usually we don't need to make any changes, right? So here the control itself will be sufficient to feed the power back to the grid. Any more questions? Any more questions?
Yes, sir, there is a question by Targan Kumar. Would you explain the TAP leg?
TAP leg and the reluctant leg is this. What is TAP means? Redundant leg, right? In some converters, they use some redundant leg for fault. For example, one fault is occurred. It is usual in the two-level inverters. We normally have some redundant leg for that. So, but in case of multi-level inverters, we have redundant units will be there in one phase. For example, here comes cascade edge bridge, right? So multiple edge bridges are connected, right? They normally connect some extra edge bridges, right? And those edge bridges are used for redundancy. Some fault is occurred. In that case, so all the power connections are or the control will be shifted to the that healthy or the redundant leg. In case of multi-level inverter, keeping a complete leg redundant, it is very costly approach. Any more
You
questions?
know,
So if you don't have any questions, again we will meet you at 3 o'clock.
Thank you, one and all. We'll come back at
And
one.
another question is which bidirectional converter is more suitable for the charging application? And as you know that most of the converters nowadays we are used for this charger is the dual active bridge converter. So one side you have H bridge and other side also you have another H bridge. So in between you have a high frequency transformer, right? So that is for power rating up to somewhere between 50 kilowatt or something. If it is a higher rating, mostly they are preferring the T-type, one side T-type and other side also T-type converters, single phase. Right. So you will discuss more in the afternoon section. Right? Thank you.
Yeah. Thank you, one and all. We'll come back again at 1:30.